Look at this idea of using symmetry to solve problems. So even functions, remember, even functions, function negative x is the same as function x. So basically, if I want to find the integral from minus a to a, I could do it if I wanted to, 2 from 0 to a, because sometimes 0 is an easy number to substitute in there, those sort of ideas. But, and I don't know if you're ever going to use this or not, but if you think about it, it doesn't necessarily have to apply for something symmetric about 0. If we've got the whole thing shifting along, then this should be true as well. If it was symmetric in the line x equals c, then if you've got c plus a, c minus a, the same idea should apply. You're going to get twice the value. Again, how useful is that? I don't know. Odd functions. This one might be more useful though. Function negative x is equal to the negative of function x. We know that one. That means the integral will be 0. You've got a bit below, a bit above, subtracts, get 0. So that shifting idea might be more useful. If you've got that rotational symmetry about a different point, but you're going from c minus a to c plus a, then you say, oh, well, that integral is going to be 0. That might save time. Will we ever use it? Who knows? The third one though, this is quite good, can make some of our integrals easier. If I want to integrate from 0 to a to function x, I will get exactly the same answer as if I'd gone from 0 to a of function a minus x. Very easy thing to prove. I just do a substitution. Here's function a minus x. If I let u equal a minus x, then du is minus dx. The limits, well, they essentially swap around. When I sub in 0, I get a, sub in a, I get 0. Therefore, that's my integral. But I can swap the limits and make that positive. It's a definite integral, so u du doesn't matter. That's the same as x dx, so they are indeed the same value. Okay, applying a shift on this one. In fact, it's also true that if I integrate from a to b of function x, I will get the same answer as if I'd integrated from a to b of function a plus b, whatever the two things added together are, minus x as well. Whilst talking about symmetry, remember, odd function times odd function will create an even function. Odd times even times even, even. So if we get an integral like this, we don't want to be wasting time using our techniques and going, oh, how are we going to integrate sine cubed? I mean, we could, but if you notice the symmetry, sine's an odd function. So I've got odd times odd, which would be an odd function. Well, okay, that's just going to be 0. I don't have to worry about integrating sine cubed. Here's where that last idea comes in handy, because expanding that out, a bit difficult, but if I change it to this, it becomes a lot easier. So this 1 minus x, I notice that number's 1 as well. Oh, hang on, I can just change that to x. And so x is basically becoming 1 minus x, if you like. But then that I can expand out, and that I can integrate, and then I can get an answer for it. Improper integrals then. A definite integral where actually what we're integrating, so the integrand, is undefined at some point in that interval, or it's unbounded. So we play with limits to see if a solution is going to exist. Something like this. So it's our hyperbola, and we want to integrate from 0 to 1, which clearly is an issue because it doesn't exist at x equals 0. So let's investigate what would happen. What's causing me the problem? It's the 0 on the bottom of the fraction. Well, what happens as n approaches 0? Of that? Well, it'll be our log function, and we get minus the log of n, but the log of 0 is undefined as well. So alright, this integral is still going to be undefined. It's not going to have an answer. But this one, if I want to integrate from 1 to infinity of x e to the minus x squared, so that's really saying, well, what's the limit as n approaches infinity from 1 to n of x e to the minus x squared? Integrate that, I get e to the minus x squared. But now if you think of that curve, e to the minus x squared, that's the classic bell-shaped curve. As x is approaching infinity, that value is approaching 0. And so we can actually get an answer for that integral, even though we're integrating up to an infinite amount. And this idea of using integration and areas to solve inequalities, this is always going to be true, of course. If you've got 3 functions, but you know that g of x is smaller than function x is smaller than h of x, then the areas under those curves must also follow that same pattern, because the biggest one would have the biggest area underneath, and so on. This one comes from the 2009 paper. So n is a positive integer greater than 1. The area of the region under the curve y equals 1 on x from n minus 1 to n, and then they've given us the two rectangles to give us that idea of, hang on, we can say the area of this big rectangle is bigger than the area under the curve, which is bigger than the area of that smaller rectangle. We're going to use that idea to show this inequality. So alright, so area of that inner rectangle is going to be less than the area under the curve. It's going to be less than the area of that outer rectangle. Do those, well, the big rectangle would be 1 times n minus 1. The smaller rectangle is going to be 1 times 1 on n, and then the middle one is the integral itself. Well, if I integrate that, I get log x. And so, all right, I have this expression. Not quite what we were trying to prove, though. We were trying to prove, let's just go back to it, e's are in there. What I'm going to do is I'm going to multiply by the n. So I've now got n log. That allows me now to get n in there. Well, why did I do that? Let's go back to what we're trying to prove. See how I've got this to the power of n in the middle. I want to try and get to the power of n. So I've got power of n, but I want e's. That's all right. I know the exponential function is continually increasing. So I can apply the exponential function to each of these pieces, and that inequality will stay the same. So e to the power of 1 would be less than e to the log, which cancels, and then on the right hand side we get e there. Well, it's almost what they wanted. If I now flip both sides upside down, I get 1 on e, flip the reciprocal, we change the sign. Now look inside the fraction, n minus 1 on n, that is the 1 minus 1 on n we were looking for. If I get the inequality signs looking nice, so in the proper order, then over here, that's going to be e to the negative of that fraction, because it's on the bottom, and of course the one on the left hand side, that becomes e to the negative 1. That's what they were asking me to go and prove. Oh wow, that finishes off our topic there. I've got some old Cambridge questions I put in there. And then of course there is the 100.